Hello, my name is Thayer Whitney. Today I will be talking about photorealistic text-to-image diffusion models with deep language understanding. So, diving into this particular paper, trying to get to the bottom of each of these different sort of areas that were discussed is honestly pretty confusing, trying to track between all the different sort of developments. So, I'm going to approach this sort of in slices. Basically, I'm going to go through describing some of the basic background information, then providing a high-level look at what happens within Imagen and its important improvements. Lastly, I'll dive a little bit more deeply into the finer details of what specifically was changed, as well as how some of the other things are specifically working, as well as take a look at what sort of pertains to improvements in this field, as well as some of the other sort of ethical questions that have arisen from this sorts of research. So Imagen is claim to fame, as it were, is sort of this better image quality, a better grasp of the context from the prompts that were provided to it. So as we can see here, the statement Greek statue of a man tripping over a cat was given to Imagen and also DALL-E 2. I'm sure many of us are familiar with what DALL-E 2 is, but DALL-E 2 is another one of these image generation sort of deep learning models. And as we can see here, looking through this, Imagen is able to pretty accurately determine the context of what is being said. The cat is always sort of in some pose, in some positioning that suggests it was getting tripped over. Same with the man. However, we can see that with DALL-E, it's getting a little confused. Some of them, the cat is being pet. Some of them, the cat is on his back, and sort of losing track a little bit here of what is supposed to be being generated. This is another example from Imagen, a black apple and a green backpack. And here we can see DALL-E 2 is sort of struggling with what object is supposed to be what color, whereas Imagen is actually properly matching the color to the appropriate object. And finally, this is sort of a more nuanced example. While they are both technically right, it is technically both a pair of glasses or a couple of glasses sitting on the surface of some table. We can see that sort of the nuance of the statement is saying that there are a couple of glasses, i.e. drinking glasses, wine glasses, that sort of idea, not eyeglasses. And we can see that DALL-E kind of gets it in the first image, but then kind of a little bit kind of loses context of what's being asked of it. So as you may have already kind of clued into at this point, Imagen is a text-to-image diffusion model. And the way that these, in a broad sense, work is there are two main processes. The first is a transformer language model. That is the thing that is actually taking the input that has been given and determining what that actually means, at least to the computer. And then the second port is the diffusion model, which is the actual model that is generating the image. And there are a lot more things that make Imagen unique, but I'm going to get to those a little bit later. So we see here pictured is the original transformer that it was designed by the team in Google back in 2017. And these have been talked about a fair bit in our class, so I will try to just briefly recap specifically as it sort of pertains to language models. The text is parsed into different tokens, and then each of these tokens is turned into a vector using word embedding. This is then fed into an encoder stage, and then using various attention mechanisms, the inputs are encoded as they relate to each other, their sentence position, etc. And these vectors are then passed into a feed-forward network. Then they are passed to the decoder. Now, in the decoder takes its output sequence and feeds it back into itself and acts very, very similarly to the input encoder. However, you need to make sure that there isn't a sort of this reverse flow of information. And so that initial input has some masking that's applied to it. And then that sort of final layer, as we can see here, it's passed out to a linear transformation, and then that final softmax layer to produce the final output probabilities of, over its vocabulary. And as I mentioned, this particular transformer is relatively old. Its original design was based in 2017, and in general, these have had some improvements made along them, but the sort of important thing to sort of think here is that the goal of this transformer is to develop a tokenization of that text to make it so that the machine, the model, has an understanding of that sort of natural language. Now, looking at the second portion of this, the diffusion model, this process starts by taking your data and gradually adding noise to that data until the data becomes so corrupted that it is in fact Gaussian noise. And during this process, you produce a set of latent variables model whose latent variables match the dimensionality of, in this particular picture, x of 0. Once this is achieved, the model is trained to denoise the image by reversing this sort of pictured Markov chain. And it's important to note that when moving between different states on a Markov chain, the next step only depends on that previous step. So it's not holding any sort of previous history in it other than just what its weights or etc. might be changing. And again, the important thing to take away from this is that the model itself is designed to be generative. So it's taking some noise as well as some other inputs, and it's coming up with new data based off the training sets that were given to it. So we'll move on now to a little bit more of a high-level overview, looking at the different sort of components that have made Imagen work, as well as sort of what makes it unique. And that's sort of going back to that first thing discussed. We were talking about the language transformer. Now, typically, when you are developing a model like this, where you're taking text input and you're producing a image output, these are typically trained by using a image text data set. However, another idea was potentially explored, because obviously that takes some significant manpower and effort to create these image sets, to go through and actually label all these. And so the idea that was presented was to use a pre-trained model trained only on a set of text to develop that sort of knowledge of what's happening and that natural language understanding. Now, in these models, they're very large, and the difference between one state of the art text encoder versus an image-based like image-to-text model was that the text model had 540 billion parameters versus approximately the 1 billion parameters for the image and text. And so what we see here is just sort of the proof in the pudding, if you will. These are based off of Drawbench, which is a human benchmark that the team developed, where the images are compared side by side, and then the raters just pick their preferred image. And so we can see here again that the people in general seem to be much more preferred of this Imagen model. And this is a more standardized score where the different encoder sizes, so the T5 small, large, XL, and XXL, were compared against each other, and they saw that as the size of that encoder, and so the T5 XXL was about 5 billion parameters. They found that as that increased, their clip score increased. However, the impact of the network size, that being the network in the diffusion model, actually did not make as much of a difference as just increasing the size of that pre-trained encoder. And again, it's important to note here that this pre-trained encoder was added and then frozen, so that they didn't go back through and tune any of the models. There was no additional adjustments to it. It was just off-the-shelf component, just quote-unquote stuck in the front, and sort of gone from there. As previously discussed, a diffusion model is a generative model that converts Gaussian noise into new data. Now, part of the process here that you can do to sort of make some gains is something called classifier guidance. And now, classifier guidance is a technique to improve sample quality while reducing diversity in conditional diffusion models using gradients from a pre-trained model. We'll say C given Z during that sampling. However, Imagen uses a classifier-free guidance, which is an alternative technique that completely avoids that usage of a pre-trained model by instead jointly train a single diffusion model on conditional and unconditional objectives via randomly dropping C during training. So here we see epsilon theta zt of C and epsilon theta z times d are conditional and unconditional epsilon predictions, given that epsilon theta given for zt minus alpha t x of theta divided by the quantity divided by sigma t, and with w being the guidance weight, we can see that by setting w to 1, this disables the classifier-free guidance, while increasing w above 1 strengthens the effects of the guidance. But during the development of this Imagen, it was discovered sort of critically to relies on this classifier-free guidance for effective text encoding. While the classifier-free guidance is an improvement, there is still some problems. Classifier-free guidance weight improves the image text alignment, but damages the image fidelity, making the images look very highly saturated and otherwise unnatural. Now, this seems due to the fact that there was a train-test mismatch arising from high guidance weights. So, in order to counter this problem, a static and as well as dynamic, which was a new technique that the Imagen team looked into, thresholding were examined. And as per memory of that sort of W in the last, we can see here these sort of what the adjustment of the weights do. So the weights varying from 1 to 5, top to bottom, we can see how that changes the image, as well as we can see what happens when there's no thresholding at all for this. So static thresholding functions pretty straightforward. It clips your X prediction to -1 or 1, meaning that if that pixel is saturated, then it's clipped. Now, that works. You do prevent the issue of just having blank images or sort of weirdly oversaturated images. However, the team behind Imagen looked into something called dynamic thresholding, an idea that they themselves had sort of put forward. And this is basically takes a value S that is set to a certain percentile of the absolute pixel value in a data set. And then if that S is set above 1, then the threshold is then set to minus S to S, and then is divided by S. And this results in pushing these sort of saturated pixels inward and preventing the pixels from saturation at each step. And you can see down below here, samples using both the static thresholding versus samples using the dynamic thresholding. The images are a lot less sort of almost like cookie cutter. If you had taken, MS Paint and outlined the picture and then dropped it onto another random background, the dynamic one is actually a little bit more blended to the light of the environment. Now, moving on to the actual diffusion model itself. The diffusion models, there are the 3 of them. They are all cascaded together. The base model is a 64 by 64, which is then fed into 2 other text conditional super resolution diffusion models to upsample that original 64 by 64 image to a 256 by 256, and then finally to 1024 by 1024. Now, this cascading design was chosen because previously it had been shown to be successful in generating high fidelity images. Imagen uses something called noise conditioning augmentation as well, which sort of similar to the idea of corrupting your data in a diffusion model anyway, corrupts the low-res image coming from the 64 model with Gaussian noise before being passed on to the next 256 by 256 model. And this proved to be critical for the team when actually trying to generate these high-fidelity images. Now, the neural network itself for each of these 3 blocks is based on the UNet design, and the UNet for the first 64 by 64 was adopted from a biomedical image segmentation algorithm. And then for the super resolution models, another UNet model, this one originally was being used for some denoising, was pretty heavily modified to improve memory efficiency, the inference time, as well as the convergence speed, which they found to be about 2 to 3 times faster. And this particular variant, the authors dubbed EfficientNet. And we'll get to that one also in a little bit. So, as discussed, this far, kind of gone through sort of high level, discussed each of the different components that are sort of make up Imagen, as well as some of the key points that are making it more unique. So I would say if you made it this far and you've enjoyed it so far, maybe bail out now, as if it's sort of going to go diving deeper into the actual math behind some of the more specific things. But I will at the end sort of be summing up the most important key points, as well as discuss briefly some of the ethics that are involved in a project like this. So for a diffusion model, diffusion models are a latent variable model with the latents z equal to the z of t, given that t belongs to somewhere in 0 to 1, that obey a forward process that z given x at the starting data of x And this forward process is a Gaussian process that satisfies the Markov structure of the process the process z of t given x is equal to the normal distribution of z of t and alpha t of x and sigma squared t of identity, as well as the process z of t given s, z of s is equal to the normal distribution of z of t and your alpha t divided by alpha s times z of s, as well as sigma squared t given s of I. Now, for the generation diffusion model is learned to basically reverse this process. And so learning to reverse the forward process can be reduced to learning to denoise that original z of t. And that z of t can be defined as approximately equal to the process of z of t given x into an estimate of x of theta for z of t, a function of x of theta, z of t, lambda of t, and c, which approximately equal x for all of t, where c is an optional conditioning signal. Now, this sort of training of x of theta using the weighted error loss is the expected value for w times lambda sub t is the L2 norm of x of theta with respect to z of t, lambda of t, and c minus x, that quantity squared. And this reduction of generation to denoising is justified as optimizing the weighted variational lower bound on the data log likelihood under the diffusion model. Now, we can use the epsilon prediction parameterization defined as x of theta for z of t, lambda of t, and c, which is equal to z of t minus sigma t epsilon 0 given z of t, lambda t, and c, that quantity divided by alpha t. And we impose a squared error loss onto epsilon theta in epsilon space with t sampled according to a cosine schedule. And in order to get this sample from the diffusion model, we start at z1 with a normal distribution between 0 and identity using a discrete time ancestral sampler and a DDIM for certain models. And the DDIM follows the deterministic update rule, which is your z of s is equal to alpha of s for x of theta given z of t, lambda t, and c plus sigma sub s over sigma sub t times z of t minus alpha sub t x of theta, where your s is less than t following that uniformly spaced sequence from 1 to 0. Finally, the ancestral sampler follows that stochastic rule for z of s, which is equal to mu sub s given t for z sub t given x sub theta, z of t, lambda of t, c, plus the square root of sigma squared sub s given t to the power of 1 minus mu times sigma squared t given s to the power of mu, that whole quantity squared, times epsilon. And if you followed that, congratulations. That took me forever to actually try to wrap my head around an even a remote amount. So taking a little bit more of an in-depth look at the so-dubbed efficient UNet modules. The UNet module, the efficient UNet was stated previously to be both simpler, it converges faster, and is more memory efficient compared to some prior implementations, especially for this sort of high resolution application. And so several modifications to the UNet architecture, such as shifting some of the model parameters from a high resolution blocks to low resolution, scaling the skip connections by 1 over the square root of 2, and reversing the order of the downsampling, upsampling operations in order to improve the speed of the forward pass. And so these several key modifications to the typical model can be seen if we go to the next slide here. So in a typical UNet downsampling block, the downsampling operation happens after the convolutions, while in the upsampling block, the upsampling operation happens prior to the convolution. And so we reverse this order for both the downsampling and the upsampling blocks in order to significantly improve the speed of the forward pass of the UNet, and they found that there was no performance degradations with this. So the most important takeaway from all of this was that the pre-trained language models are very effective as these text encoders. And it showed that the most performance gains in the system was from using these particular models. And while there are some other important components, the usage of the free classifier, free guidance, and the dynamic thresholding stuff, the novel approach to using the text encoding is definitely the most important. So all of this is well, fine, and good, but it does sort of start raising some ethical questions that the team sort of mentioned towards the end. And in various sort of public and academic discourse regarding appropriate use of public data has raised concerns regarding particular data subjects like awareness and consent, because oftentimes these sort of data sets, they are just simply scraped from the internet, and they may contain images of content that would be probably best left out of the system. Sort of in recent memory of the IBM Watson, I say this as my own memory of this, not what the authors have said, but the IBM Watson was given access to the Urban Dictionary, and it turned out to be somewhat unpleasant after that fact. Sort of the content of these data sets is often uncurated, and so it's very easy for harmful data to enter these models. The team found that in a particular audit of one of their training sets, because some of their training sets, they did have sort of curated data, but in one of the ones that wasn't like that, they found a number of different pornographic images, different slurs, as well as some other harmful social stereotypes. And again, there's been some concern raised over these problems relating to the data subject. And so in the end, the authors made the final determination to not release Imagen, as they felt that they were ethically bound to limit the repercussions of these generative machines. So thank you very much for listening. It's been a pleasure, and I'll see you in class on Tuesday.